In section 2.2, we study how Dalton's atomic theory evolved. Dalton's atomic theory stood largely unchanged for almost 100 years, and then at the beginning of the 20th century, that's the 1900s, there were a series of discoveries that were made that really kind of led us to our current understanding of how atoms are constructed. The first important experiment that led to the discovery of some structure within the atom was performed by J.J. Thomson right around the beginning of the 20th century. J.J. Thomson was playing around with what were then known as cathode rays that are emitted from charged plates. So basically what you would have is a long glass tube out of which you had pumped almost all of the air. So we call this a vacuum tube. And at one end of the tube, you have a plate that is connected to the negative terminal of a battery. And then adjacent that, you have another electrode that is made positive, but that electrode has a slot in it so particles can pass through it. At the far end of your tube, you coat it with a material like phosphorus that glows when a charged particle hits it. So what is found when you turn this on is that particles are emitted by the cathode and hit the screen at the far end of the tube. Now, because these particles are attracted towards a negative plate, these particles must be negatively charged. Now, Thomson was really clever. People knew about these, but they hadn't really done much work in understanding what these rays were. What Thomson did was he made these rays move around using magnets and a second set of charged plates. So he could attract them towards a positive plate or repel them from a negative plate, and he could vary the voltage and make these guys move around as much as he wanted to. He could bring magnets closer and further apart from these rays and again make them move around. And he took a bunch of careful measurements, and he was able to figure out that these cathode rays were composed of negatively charged particles and that had a mass to charge ratio that was a lot smaller than anything that you would have observed for any known atom. So out of all of this work, Thomson was able to get the ratio of the mass to the charge for this particle, and it appeared to be very small. So this was evidence that there was some kind of subatomic particle, some kind of like part of an atom. So he proposed that these cathode rays were subatomic particles, which we now call electrons, and which we normally will give the symbol lowercase e superscript minus. So obviously this violates Dalton's atomic theory because we're now saying that atoms have parts, right? So this leads us down the development of towards the development of a new atomic theory. Now, having the mass to charge ratio of an electron is not very interesting. What we really want is the mass of the electron. So if we can get the charge, we can combine that with Thomson's mass to charge ratio and we can get the mass. So a guy called Richard Millikan, who was an American physicist, he figured out the charge on the electron, and we'll talk about how he did that in a moment, and he found it to be negative 1.6 by 10 to the minus 19 coulombs. So he then multiplied Thomson's mass to charge ratio by this charge, and he gets the mass of the electron. And the mass of the electron is tiny, 9.1 by 10 to the negative 28 grams, which is less than 1/1000th of the lightest known atom. So that's pretty cool, right? We now have completely characterized the first subatomic particle, which is the electron. We have its charge and its mass. So we're just going to allow ourselves to get sidetracked and look at how Richard Millikan actually figured out the charge on the electron, because it's kind of cool. What he did was he produced oil droplets. And these oil droplets were of a consistent mass, and he was able to induce on them an electric charge. He used either friction or X-rays to generate an electrical charge on the oil droplets. He would allow the oil droplets to fall under the influence of gravity, but because they were charged, he could put plates either side of where the oil drops were falling and vary the charge on those plates until the oil drop would levitate. And what he found by doing this, by balancing the gravitational pull downwards and the repulsion upwards, was that the charge on his oil drop was always a whole number multiple of negative 1.6 by 10 to the minus 19 coulombs. So what he decided was that that was the smallest possible unit of electrical charge, that this is the charge of the simplest particle that's found in an atom. So he combines this information with what Thomson had discovered earlier, and he gets the mass of the electron as well. And the mass of the electron, if you recall, was 9.1 by 10 to the negative 28 grams. So an electron is very, very tiny. So at this point, we know about the existence of the electron, and we have completely characterized it in terms of its electrical charge and its mass, but what we don't know is how the electron is positioned within the atom. So from these results, Thomson proposed what is now referred to as the plum pudding model of the atom. And so this is probably like the simplest sort of model of the atom that you could come up with. What you have is a big ball of matter, which is positively charged and is quite heavy. And then embedded in that ball of positive charge are the tiny little light electrons. So yeah, that's it. That's how it happens. And you have as many negative charges as you do positive charges. So overall, the atom is electrically neutral. Now, he called it a plum pudding because a familiar food to him was a pudding made with plums that was normally eaten at Christmas, which was a big ball of dough with tiny little raisins embedded in it. If he lived in the 21st century, he probably would have called it something more like, a chocolate chip muffin or something like that. But that's what the food that he was familiar with. So people were like, okay, we're not really getting a lot of information about the structure of the positive part of the atom. So simultaneous to this, people like Henry Becquerel and the Curies, and Ernest Rutherford were looking at radioactive decay, and they had observed that some atoms spontaneously emit subatomic particles. And there were two types of particles that they had detected. There were beta particles and there were alpha particles. Alpha particles were discovered first, beta particles were discovered second. And it became obvious quite quickly that beta particles were just simply high energy electrons. Alpha particles, though, were a bit more of a mystery. It was known that alpha particles are positively charged. It's also known that they have twice the charge of an electron and a mass of about 4 times that of a hydrogen atom. So these guys are also moving very, very fast, hundreds of thousands of meters per second. So they're heavy and they're moving quick. So Ernest Rutherford came up with the genius idea of what about if we took a beam of alpha particles and fired it at some atoms? Perhaps the way the alpha particles scattered would tell us a little bit about the structure of an atom. So he had 2 of his students, Geiger and Marsden, perform the following experiment. So what they did was they took a beam of alpha particles and they fired it at a gold foil. And the assumption was that the alpha particles were so heavy and were moving so quickly that they would go straight through the gold foil like bullets through tissue paper. And he did some math about what the density of an atom according to the plum pudding model would be, and then compared that with the speed of the alpha particles and came up with this conclusion. So Geiger and Marsden headed off to the lab to test this idea. So what they did was this. They took a piece of radioactive material that was known to emit alpha particles. They put it into a lead box that blocked most of the alpha particles from leaving the lead box, but it had a little pinhole in it. So they end up with a beam of alpha particles. They fired the beam of alpha particles at a gold foil, and they chose gold because gold can be hammered until it's just 1 or 2 atoms thick. So any alpha particle is only going to hit 1 or 2 atoms. Around their gold foil, they set up a screen that had been coated with a material that glows when a charged particle hits it, similar to what J.J. Thomson did when he was looking for electrons. And so they're going to be able to see by flashes of light where the alpha particles arrive or are scattered. Now, remember what they were expecting is that most of the alpha particles or all of the alpha particles should go straight through undeflected. What they actually observed was that most of the alpha particles did go straight through, but a few of them were deflected to quite high angles, and some of them even came all the way back every now and then. So this was definitely a little bit surprising because alpha particles, again, 4 times heavier than a hydrogen atom, and they are hustling. So you could think of this as being like if you were firing a machine gun at a piece of tissue and every now and then a bullet bounced back and hit you. So this was, as I said, somewhat surprising. So Rutherford spent a few years trying to figure out what these results meant. So he realized fairly quickly that as most of the alpha particles pass through the foil completely undeflected, as though there is nothing there, then atoms must be mostly empty space. Now, some of the alpha particles are deflected or bounce back. So he interpreted that as being that the atom must have a positively charged nucleus. It has to be positive because it's repelling the alpha particles, not attracting them. And because it was able to bounce back these very fast-moving alpha particles, that positive nucleus must contain nearly all of the mass of the atom compressed down to a tiny, tiny speck. And he spent a long time calculating how dense the nucleus of the atom might need to be in order to stop an alpha particle and send it back in the other direction. So, doing these calculations, Rutherford was able to predict the size of an atom and its nucleus. So Rutherford said that the atom has a total diameter of about 10 to the minus 10 meters, but the nucleus represents just 1/100,000th of that diameter and has a diameter of about 10 to the negative 15 meters. So if you imagine an atom to be Husky Stadium, then the nucleus is like a marble in the middle of Husky Stadium. And remember that that marble contains basically all of the mass of the atom. So what takes up all of the space that isn't the nucleus? Well, it has to have very little mass because most of the mass is in the nucleus, and it has to be negatively charged to counter the positive charge of the nucleus. So, it seems that a likely candidate are the electrons of the atom, right? So, Rutherford said, I think that atoms are organized as follows. That the positive charge of the nucleus is a result of positively charged subatomic particles that he calls protons. And that the small negatively charged electrons move around the nucleus at a great distance from it like planets around the star. But planets are held in place as a result of the attraction of gravity between a star and the planet. The electrons are held in place as a result of the electrical attraction between the negative electrons and the positive protons. However, Rutherford couldn't quite get enough mass into his nucleus in order to completely stop an alpha particle and turn it around and make it go in the other direction using only protons. It was Rutherford's student, James Chadwick, who was studying radioactive decay, who recognized that there must be a second particle in the nucleus that had no electrical charge. He calls this the neutron. And so that now completes the model of the Rutherford or planetary model of the atom. So we have a nucleus containing protons that are positively charged and neutrons that have no electrical charge, that contains almost all of the mass of the atom. And then at a great distance from that, we have electrons, which are negatively charged and very tiny, orbiting the nucleus, and they are held in place via the electrical attraction between the positive nucleus and the negative electrons. So that completes the planetary model. And then everything that kind of comes after that is just an improvement on this model. And we're going to continue studying the improvements of this model throughout the general chemistry sequence. So let's look at some problems from the OpenStack book. It says, how are protons and neutrons similar? Well, I think how they're similar is that they are both located in the nucleus. And how are they different? Well, how they are different is that neutrons have no electrical charge, and protons are positively charged. Okay, so let's see what the answer key tells us. It says both are subatomic particles that reside in an atom's nucleus. Got that. Both have approximately the same mass. Well, we didn't say that, but okay. Protons are positively charged, whereas neutrons are uncharged. Perfect. Okay, so that concludes section 2.2, which basically describes the development of the Rutherford model of the atom.